Hello, my name is Daniel Smullen, and I'll be introducing our work today called The Best of Both Worlds, Mitigating Trade-offs Between Accuracy and User Burden in Capturing Mobile App Privacy Preferences. This work is coming out of Carnegie Mellon University from Pittsburgh, Pennsylvania. Let's get started. Android is an incredibly popular mobile operating system, and it continues to rise in popularity. Android is also increasingly sophisticated, with new phones introducing new functionality, sensors, APIs, and smart features all the time. As of KitKat, sensitive APIs are moderated in Android by privacy settings called permissions. These permissions appear in the form of dialogues that allow users to choose whether to allow or deny access at the time that the permission is first requested. Runtime app permissions are especially important and useful because prior to their existence, that is, prior to Android KitKat, users could only choose to moderate access to the sensitive data exposed by these APIs by choosing not to install the app. So this was quite a big improvement. However, data continues to be collected and used in ever more diverse ways, on the phone, in cars, even on the web, and users are expected to make an increasingly unrealistic number of privacy decisions. Access to sensitive APIs are regulated by permissions in the mobile context, and so for each app, each sensitive data category requires a permission decision. This creates a fundamental trade-off between the accuracy of permissions and user burden. That is to say, the more accurate a mobile app permission is, one that can express the user's preferences in the type of granularity that they expect, the more questions are required in order to burden them. Now, in this case, prior research shows that purpose should be included as part of these mobile app permissions, but included in it would be even more questions that are even more burdensome. Here in this example, we see one of the apps that can be found on the Google Play Store. And this app is called YouTube Gaming. We can see that Google's Play Store app lists all of the different permissions that can be requested by the app, and this is listed when you install it. This shows the difference between apps permissions that are requested at the install time and those that are requested later during runtime app permissions. In this case, we can see that some of the install time permissions include identity, and some of the runtime app permissions, those that are requested the first time that the app needs access to them, are those such as contacts, location, camera, and so on. Unfortunately, the Google Play Store doesn't actually make a clear distinction between which ones of these are runtime app permissions and which ones of these are install time app permissions, but this is cleared up somewhat in this example, which actually shows the current permissions manager that's provided by Android. And in this case, you can see that all of the permissions which are allowed or denied at runtime can also be reviewed and can be changed later on. However, despite the fact that study after study shows that people care about privacy and privacy management, users generally tend not to engage with privacy management because they simply find it too burdensome. There's an unrealistically high number of permissions, and the existing permissions don't capture purpose. In fact, purpose does matter, as shown in prior literature, but if people were to be able to express their permissions subject to purpose, there would be an explosion of new permissions.
In fact, in the case of Android, if you were to simply trivially extend the current model by incorporating new purposes, even if you were to introduce a small number of purposes, such as 3 new purposes, you'd have to multiply the number of questions that would be asked of the user by 3. In our study, we focus on 3 purposes in particular. One, which is where the app actually requires the permission to perform its own internal functionality, another covering advertising, and another covering a general catch-all category.
So this raises a fundamental question. How do we reconcile the fact that preferences are complex, including being purpose dependent, and even without purpose, the number of settings are already unrealistically high? This led to the research questions in our study. First, what is the impact of purpose and other contextual factors on the predictive power of machine learning models for Android permission preferences? Second, what effect does this predictive power have on the accuracy of recommendations made by privacy profiles? And finally, can we make better predictions without increasing user burden?
Our work shows that machine learning can mitigate the trade-off between accuracy and user burden. Finer-grained settings result in a much larger space of settings. On paper, there will be even more settings in these more complex models that introduce additional contextual factors. But permission subject to purpose let us better capture people's settings. The literature shows that these permissions are more in tune with users' expectations of privacy, and we show that they have added predictive power. The main contribution of our work, therefore, is to demonstrate that moving towards models that are more fine-grained, such as those that take into account purpose and other contextual factors which we know are important, can improve upon accuracy, but without creating additional user burden. Our surprising finding, however, was that the added complexity that these additional factors added to the model were able to be leveraged by machine learning and have better predictive power, which in fact reduces overall user burden. We can see that the machine learning can take advantage of these more accurate settings to build models that are better at anticipating people's privacy preferences, and these models can provide recommendations which in turn reduce user burden. Thus, the heaviest burden of permissions management is taken up by the machine learning instead of shifted to the user.
Now I'll go into a little bit of related work.
One very important difference between our work and some of the prior literature is the study of purposes. Purposes as a contextual factor in privacy are often seen in the literature, and in fact, prior work has studied purpose in smartphone permissions, finding complex relationships between the stated purposes for using a smartphone permission and how this purpose may influence user behavior. In our study, we quantify the user burden and accuracy trade-offs that are inherent in more complex permissions models that use purpose. In particular, we explore how machine learning can mitigate the user burden and accuracy trade-off by taking advantage of the predictive power of finer-grained settings.
Prior work in Android has studied privacy managers of different types and displaying different types of information, some using notifications, some using nudges, and some using different types of data, helping users to gain a better understanding of what their permissions management decisions entail. Also, a prior work used the profiling approach that we also used in our methodology. Profiling is quite simple and can be divided up into three major steps. In the first step, users provide their settings. Generally, this is done through large-scale surveys, but these settings can be collected in any number of different ways, such as by capturing them from those that opt in on their phones using permissions management apps, or using large-scale crowdsourcing, such as on Amazon Mechanical Turk. Next, these settings are then clustered, and users are clustered together based on features extracted from their settings. And finally, each cluster has an associated set of recommended privacy settings. These are called profiles. Our methodology is a little bit different, and I'm going to go into the details about how our methodology differs from prior work. First, our study surveyed Android users at scale. We used crowdsourcing on Amazon Mechanical Turk to collect preferences to allow or deny app permissions for a wide variety of mobile apps. Then we collected demographics about the users because we had an intuition that perhaps these demographics may also correlate with expressed preferences. Next, we performed analysis of the survey data using regression modeling and hypothesis testing. We did this in order to expose what factors had a statistically significant effect on the expressed preferences of users. Finally, we took this large corpus of data and used it to build and analyze privacy profiles. In doing so, we performed a sweep of the parameter space. We then, after each sweep, examined how accurate the predictions were of our profiles, and we also examined how many user interactions would be required to both organize users into profiles and to ask users questions after the fact in the instances upon which the profiles were not able to make confident recommendations to users about what their settings probably ought to be. In the first step, we surveyed the Android users using questions as can be seen in the lower left corner of the screen. In general, we collected 5,964 observations of users' privacy preferences according to 3 Android permissions. The first was calendar, moderating access to the user's calendar, whether that's Google Calendar or other calendars that are located on the Android device. The next was location, which, as of the current versions of Android since KitKat, includes both fine-grained and coarse-grained location services. And the third sensitive Android permission was contacts, or the contact list and contact details of all the users that are stored on the device. We then gathered these permissions for an app corpus of 108 apps across all of the categories of apps found in the Google Play Store. And finally, we collected 994 samples from Android users in the United States over the age of 18. In the second step, we analyzed the survey data, exploring what factors had a statistically significant effect on the expressed preferences. And the list of regression models that were found to be significant can be seen below. This includes factors such as app familiarity, which measured how familiar the user self-expressed they were with the specific apps being surveyed about. But we also found significance in other more surprising categories, such as the participant's age, their education level, and the city size, among others. These regressions showed that when these factors were statistically significant, they increased the predictive power of the model to make accurate recommendations about what the user's privacy preferences are likely to be. And most importantly, the first that we found on the list was that the purpose for the permission was especially significant. The intuition is as follows. You can see the regression table for purpose in the lower left of the screen, and you can see that it's divided up into 3 sections. There are also 3 further subsections corresponding to the 3 different types of permissions, that is, contacts, calendar, and location. And we found that across all 3 of these permissions, the same factors were found to be significant. That is to say, the null model versus advertisement, the null model versus other unspecified, but not the null model versus internal. What does this mean? We captured preferences according to 3 different purposes. The first one was internal. In other words, the app required these permissions in order to provide its basic internal functionality. The second and third categories of purposes were for advertising purposes, and the third was for other, or explicitly stated as unspecified. The null model represents a model where there is simply no purpose that's specifiable. No purpose is taken into context at all, very much the same as what can be seen in the current model of app permissions. And what we found was that people's preferences changed in a statistically significant manner when the purpose was advertisement or other or unspecified compared to the null model. However, users' preferences were not statistically significantly different in the case where they were specified as internal. What is the interpretation of this? We reason that this implies users expect that the permissions are required by the app when there's simply no way to specify why the app actually needs the preference, as can be seen contrasted between the 2 modes of display on the right and on the left. This implies that users are expecting that if the app is asking for the permission, it must actually need it to work. However, in reality, very often this is not the case. The third step was to build and analyze privacy profiles. One can see in the scatter plot on the lower left-hand corner the relationship between the accuracy of the predictions that profiles made about users' preferences, and on the x-axis, the average number of user interactions. Naturally, higher accuracy is better, but lower average numbers of user interactions are also better. And what we found was that the model, which included purpose, an entirely new dimension in the model, therefore making it far more complex, was in fact not only more accurate overall, but also required fewer average user interactions overall. This can be seen highlighted in the yellow area of the graph. whereas the purpose-independent model, which is similar to the current Android model, can be seen in the blue highlighted area. The number of user interactions is further explored on the graph located on the right-hand side, where the interaction types are shown in the legend below. The blue line represents the number of questions required to ask a user after the fact when the profiles are unable to make accurate recommendations. The red line represents the number of questions required to actually profile the user and organize them into one of the K profiles. And finally, the yellow line shows the sum of the other two red and blue lines. And what can be seen in the top graph is that the efficiency of the model, which includes purpose, is actually much higher across almost all values of K than the model which does not. This shows that even with more complex permissions models, that is to say, those that include the extra dimension of purpose, the machine learning has enabled higher accuracy, but also with fewer overall user interactions.
This important finding was the inspiration for our title, The Best of Both Worlds. You get the best of both worlds when you get both increased accuracy and also minimized user burden. Our work can be summarized as follows. First, we started with a large-scale survey on Amazon Mechanical Turk, where we collected permissions preferences for a wide variety of apps across all Google Play Store categories from 994 users in the United States. Next, we performed logistic regression analysis and hypothesis testing to determine which contextual factors were statistically significant. Next, we performed clustering and data mining on the resulting corpus of data. We clustered based on significant factors found in our regression and used this to generate profiles. These profiles would then make recommendations for permissions that users would be likely to use. Finally, we performed evaluation on the profiles. We used the profiles to test predicting participants' preferences for the apps, and we tested different numbers of profiles, or different values of K, from 2 through 40. In doing so, we measured the number of questions required to initially organize an individual into a profile, then next measured the number of extra questions required when a profile was unable to make a recommendation. What we showed was that machine learning leveraged the additional predictive power in more complex models, that is, those that included purpose and other contextual factors, to make better recommendations, which were more accurate, while at the same time burdening users less.
Thank you very much for listening to this presentation. For more information, please visit our website at privacyassistant.org to see more about the Personalized Privacy Assistant project. You can also see the contact information for the authors here. The corresponding authors are listed with an asterisk. Also, we would like to acknowledge DARPA, the Air Force Research Laboratory, and the National Science Foundation. Our study was supported in part by grants from these organizations. Thank you.